Have you ever wondered how a massive file gets zipped down to something you can actually email? Or how images get compressed without turning into a pixelated mess? Well, today, we're going to pull back the curtain on one of the cleverest algorithms that makes it all happen, Huffman coding. Let's dig in and see how it works its magic.
So here's the plan. We'll start by looking at the basic problem that needs solving. Then we'll talk about a greedy solution, and we'll actually build something called a Huffman tree step by step. After that, we'll see how to get our compressed codes from that tree, and finally, we'll look at the secret sauce, the one rule that makes the whole thing work flawlessly.
Okay, so first things first. What's the actual problem with how we usually store text? Well, think about any language. Some letters pop up all the time, right? Like E or A, and others, like Z or Q, are way less common. And that imbalance, that's the key. It creates this huge opportunity to be way more efficient.
See, most standard systems, like ASCII, use what's called a fixed-length code. It means every single character, whether it's super common or super rare, gets the exact same amount of space, usually 8 bits. It's simple for sure, but it's also incredibly wasteful. So the big idea behind Huffman coding is to flip that on its head and use variable length codes. Give the common letters nice short codes and give the rare letters longer ones. It just makes sense, right?
And that leads us to the million-dollar question. It's not enough to just randomly assign short and long codes. To get the absolute best compression, we need a reliable system, a method to generate the perfect, the optimal set of codes for any chunk of data. So how do we actually do that?
Well, the answer lies in a really cool strategy called a greedy algorithm. And you gotta love the origin story. It was actually figured out by an MIT student who was just trying to avoid taking a final exam.
At its core, that's what Huffman coding is. It's a greedy algorithm, and its goal is beautifully simple. Create the best possible compression code. And it does this by making sure the characters you see all the time get the shortest possible binary codes, and the ones you barely see get the longest ones. This way, the total size of the file shrinks as much as it possibly can.
So what do we mean by a greedy algorithm? It's actually a pretty intuitive idea. It's an approach that at every single step just makes the choice that looks best right now. It doesn't try to think 5 steps ahead or see the big picture. It just makes a series of these small, locally optimal choices and hopes, and in this case it's a very good hope, that they'll all add up to the best possible overall solution.
And here's that story I mentioned. Back in 1951, David Huffman was just a student at MIT. His professor offered the class a choice: take the final exam or write a term paper on finding the most efficient way to represent characters using binary code. Huffman went for the paper, but he struggled with it for months and was just about to tell his professor he was giving up. Then, suddenly, he had this breakthrough. What if you built the code from the bottom up, using a binary tree based on frequency? And just like that, this simple, greedy idea cracked a problem that had stumped even his professor.
Okay, now for the main event. Let's roll up our sleeves and actually see how this works. We're going to build a Huffman tree from scratch. We'll use a simple example with just 4 characters, each with a different frequency, and watch how the algorithm builds the perfect code for them one step at a time.
Here's our data set for this example. We've got 4 characters. We have A, which shows up 20 times. We have B at 40, C at 60, and our most frequent character, D, at 80. Our mission is to use that greedy strategy to build a tree that gives us the absolute most efficient codes for this exact set of frequencies.
The whole process starts with that simple, greedy choice we talked about. You look at your list of characters and you just pick the 2 with the lowest frequencies. Easy. In our case, that's A with a frequency of 20 and B with a frequency of 40. So we take those 2 nodes, A and B, and we merge them. We create a new parent node just for them, and the frequency for this new parent is just the sum of its kids. So 20 plus 40 gives us 60.
And just like that, our list of active nodes has changed. The original A and B are now tucked away inside their new parent node. So our new list, sorted by frequency, has our combined A plus B node at 60, the character C, which is also at 60, and D at 80.
And now, we just do it again. It's the same exact move. Look at the current list and find the 2 nodes with the lowest frequencies. This time, we have a tie. It's our new combined node and the character C. Both have a frequency of 60, so we grab them.
And just like before, we merge them together. We create a new, even higher level parent node. Its frequency is, you guessed it, the sum of its children. 60 plus 60 gives us 120.
And boom, our list gets even smaller. We're getting close now. We're down to just 2 nodes left in our list, the character D with its frequency of 80, and our big combined node with a frequency of 120.
All right, here we are, the final step of building the tree. We take the last 2 nodes we have, and we combine them.
And there you have it. These last 2 nodes get joined together to create the very top of the tree, the root, which has a total frequency of 200. And our tree is now complete. You can see all of our original characters are the leaves at the bottom, and everything is connected under this one single root.
The hard part is totally done. Now that we have our finished Huffman tree, we can use its shape, its structure, to generate the unique binary code for each character. This is where we finally see the compression happen. So how do we get the codes from this tree? It's actually a super simple rule. Starting from the root at the top, anytime you go down a branch to the left, you write down a 0. Anytime you go down a branch to the right, you write down a 1. That's it. A character's final code is just the path of 0s and 1s it takes to get from the root all the way down to that character's leaf.
So let's trace the paths on the tree we just built. Look at D, our most frequent character. Its path is just one simple branch, so its code is just 0, super short. Now C, its path is 2 branches, giving it the code 11. And now look at A and B, our least frequent characters. They're buried deeper in the tree, so they need 3 branches to reach them, giving them codes of 100 and 101. The algorithm worked perfectly. The most frequent character got the shortest code.
But wait, there's one last crucial piece to this whole thing. If you have all these codes of different lengths and you string them all together, how does a computer know where one character's code stops and the next one starts? This is solved by an absolutely amazing property that just naturally comes out of the way we built the tree.
This property is called a prefix-free code. It sounds technical, but it's simple. It just means that no code is the beginning of another code. Look at our list. The code for D is 0. But notice, no other code starts with a 0. This is guaranteed because in our tree, every single character is at the very end of a branch. It's a leaf. You can't go any farther. This brilliant little detail means the computer can read a long string of bits and decode it perfectly with 0 confusion.
And that really is the elegance of Huffman coding. It's this amazing example of how a very simple, almost naive, greedy approach, just picking the 2 smallest things over and over again, can lead to a provably perfect optimal solution. And it kind of makes you wonder, right? Where else out there in technology or even in nature do these simple, in-the-moment choices end up creating the best possible outcome for the whole system?